You know how your phone can translate a sign in real time? Or how your camera can just instantly pop a complex filter on a photo? That is some serious AI power running right there on your device. But it also brings up this huge engineering puzzle. I mean, think about it. The AI models that do all this magic are absolutely massive. They're trained in these giant data centers on legit supercomputers. So how in the world do we take all that brain power and squeeze it onto the tiny battery-sipping chip inside our phones, or our cars, or our smart speakers? Well, when you try to run these giant AI models on a little device, you hit three major roadblocks. First, latency. You need an answer now. Nobody's going to wait 5 seconds for a sign to translate. Second, power. A huge model would just suck your battery dry in like minutes. And third, the computational cost. Our devices just don't have the raw horsepower of a data center. Not even close. To solve this puzzle, engineers came up with this incredibly elegant trick. It's a kind of shortcut that makes all of this on-device magic happen. It's called neural network quantization. So what is it, really? At its heart, quantization is basically a compression tool, but for numbers. Think of it like this. You take a gigantic, super high-resolution photo, and you save it as a smaller JPEG. Yeah, you might lose a tiny, totally unnoticeable bit of detail, but the file size just shrinks like crazy. Quantization does the exact same thing to the numbers that make up the AI model's brain. So here's the deal. Models are usually trained using these big, super precise 32-bit floating point numbers. Numbers with lots and lots of decimal places. Quantitation takes them and converts them into much smaller, simpler 8-bit integers. We're talking just plain old whole numbers. We're giving up a tiny bit of that precision to get a massive boost in efficiency. And the benefits? Oh, they are immediate and they are big. First up, memory. Just by switching from 32-bit down to 8-bit numbers, the amount of space the model takes up on your phone gets cut down by 4 times. All of a sudden, it's a way smaller, way more manageable file. But here, this is where it gets really exciting. The speed. It all comes down to how the silicon in the chip is actually built. It turns out that doing math with simple whole numbers is way, way more efficient than with complex decimal numbers. And this can lead to a speedup of up to 16 times for the most important operations. That's a huge performance gain. But, of course, there's a catch. There's always a catch, right? This shortcut isn't free. Losing all that precision, rounding all those numbers, it introduces noise and error into the network. And sometimes, those errors can lead to a complete and total collapse. This slide shows the problem perfectly. So imagine the original precise values are those black lines. They can be anywhere on that smooth line. Quantization forces them to snap to a much rougher grid of possible integer values, which are the blue lines here. This can create rounding errors. And if a value is way out there, it just gets clipped off entirely. You're just losing valuable information. So just how bad can it get? Okay, check out this data for a popular AI model called MobileNet V2. In its original form, it's almost 72% accurate. Pretty good. But after a simple, naive quantization, its accuracy plummets to 0.12%. It's become completely useless. It's no better than just guessing at random. The shortcut totally broke the AI. So is quantization just a failed idea? Not even close. This is where the real engineering genius comes in. Researchers developed this whole set of clever repair techniques called post-training quantization, or PTQ. Think of it like a specialized toolkit for fixing the damage. And the best part is, you can do it all without having to retrain the entire model from scratch. Inside this toolkit, you've got 3 main instruments. First, cross-layer equalization. It basically rebalances the numbers across the model to make sure no single part is too sensitive to rounding errors. Second, bias correction, which cleans up any predictable shifts in the output caused by those errors. And finally, something called A-to-round, which is a much, much smarter way of rounding numbers. We'll get to that in a second. Let's see that first tool in action. Remember our broken MobileNet V2, sitting there at a pathetic 0.12% accuracy? Well, just by applying cross-layer equalization, the accuracy rockets all the way back up to nearly 70%. This one technique alone basically rescues the model's performance almost completely. It's amazing. And now for A-to-round. This is such a clever idea. The simple, kind of dumb way to do this is to just round to the nearest whole number every time. That's the red X on the chart. But that's not always what's best for the model's final answer. A-to-round is smarter. It actually tests out different rounding choices, those are the blue dots, to find the one that gives the entire network the highest final accuracy. It's not about being closer, it's about being better for the final result. But the real power, the real magic, comes from putting all these tools together. Engineers don't just use them randomly. They've built a standardized, reliable process, a pipeline, that consistently delivers incredible results. And this is what that pipeline looks like. It's essentially a step-by-step recipe for success. You start with your big, pre-trained model, you use cross-layer equalization to get it ready, then you use methods like bias correction and aid-around to fine-tune everything. This robust process is the key to making AI models small and fast without breaking them. And the payoff? Well, it's crystal clear. Just look at this table. You can see that with the full PTQ pipeline, a whole bunch of different AI models, from image models like ResNet to complex language models like BERT, can be converted to 8-bit with almost no drop in performance. Look at Inception v3. Its accuracy actually goes up a tiny bit. We get all the awesome benefits of a smaller, faster model with basically zero downside. So, the next time you use an app that seems to do some impossible AI trick instantly on your phone, you'll know the secret. It's this hidden engineering, this brilliant process of quantization and repair that's chugging away behind the scenes, making it all possible. And that kind of leaves us with this one fascinating final thought. This whole field is a constant race between the ever-growing power of AI and the physical limits of our devices. As these models get exponentially more powerful, the challenge just gets bigger and bigger. So what new, even more ingenious shortcuts will engineers come up with next to keep all that incredible intelligence running right there in the palm of your hand?